All right. This is 4.2. The mean value theorem. Yeah. So this is 4.2. And this is called the mean value theorem. And before we get to that theorem, we're going to do some other things first. We may get there today. We may have to hold on that one tomorrow. But I want to re-emphasize the importance of actually knowing the theorems by name, because I feel like that makes them make a whole lot more sense than if you just scramble a whole bunch of letters and then try to figure out what we're talking about. We're going to open this lesson not by talking about the mean value theorem, but by talking about one of the theorems that leads up to the mean value theorem. So for right now, 306. For right now, we're going to introduce what's called Rolle's theorem. Rolle's theorem. So I want you to write this down. It says, let f be a function that satisfies the following three hypotheses. 1, f is continuous on the closed interval from a to b.
What's this one called?
Rolle's theorem. ROLLE'(s). Rolle's. Let f be a function that satisfies the following three hypotheses. 1, f is continuous on the closed interval from a to b. So you've got to prove continuity. Secondly, okay, you got it. Pause. Yeah. You got it. All right. Number 2, f is differentiable on the open interval from a to b. So we're not looking at any sharp turns or any cusps or any situations where we wouldn't be able to differentiate. Remember that continuity doesn't always imply differentiability. Absolute values are continuous. They are not differentiable everywhere. And then the last one, number 3, is kind of what makes this theorem. What it's saying is f of a is equal to f of b. F of a is equal to f of b. So we're on an interval from a to b. And f of a is equal to f of b. So what does that mean? The y values are the same on the endpoints. So the y values are the same on the endpoints. He says it's like a parabola. Could be. What else could it look like? A straight line? Sure. So let's get some cases here, and I'm just kind of copying these straight out of your textbook. There's 4 different cases for what this might look like. We could have from A to B, we could have a horizontal line. From A to B, this is kind of option A. Option B, we could have something that has a maximum between A and B. We could have something that starts at A and goes up and comes back down and then comes back up to B. And lastly, we could have something that looks like an upside down parabola-ish. Okay. So these are 4 different cases where this is true. F is continuous, F is differentiable, and I start and end at the same height. In all of these, f of A is equal to f of B. Start and end on the same level. Okay. If that's true, then Rolle's theorem says there exists a number C on this interval where f prime of c equals 0. So it doesn't matter how it rolls in between A and B, as long as it starts and ends on the same level. There's some letter C, some number C in the middle between A and B where the derivative is 0. Okay? So let's identify that point on A to B on part A. Where do you think that would happen? The whole time, right? That happens all the way through. This says then there is a number. Yeah, there could be a lot of numbers. You're guaranteed at least one. There is a number between A and B where f prime of C equals 0. That's saying where the derivative at that value is 0. And you can see I've got a horizontal tangent line because I'm dealing with a horizontal line. That's true on all values between A and B. Okay. Let's identify where that might happen between A and B on part B. What does it feel like? Find yours. Okay, yours may be a little different than mine based on how we drew. But we're able to say that at some point C, f prime of C is 0. It happens twice on my C. I'll call that first one C1, and I'll call the second one C2. And on my D, it happens to be a minimum value. Okay. Rolle's theorem is also an existence theorem. It tells you that there exists a number. It doesn't tell you how to find it. Okay, it doesn't tell you what it is. It just says that you're guaranteed to have some place in there where the derivative is 0. Okay? Okay, so let's go on to example 1. Before you can use Rolle's theorem, you've got to do what? What do you have to prove? Okay, you have to prove that it's continuous, therefore differentiable, and that A and B are equal. Before we can use Rolle's theorem, we have to prove that f of A equals f of B. Okay, so let's look first at the function. It says let f of x equal x cubed plus 3x squared minus x minus 4. And we're looking on the interval from -3 to 1. So there's my A to B. They could have written it as -3 to 1 with inclusive intervals. 1, is it continuous?
Yeah.
How do you know?
It's polynomial.
It's a polynomial function. Polynomial, therefore continuous. Okay. And are there any sharp turns, any places, any asymptotes, any places in here? We've already said it's continuous. So there's no reason that it wouldn't be differentiable also. Okay, you've got to give those justifications. This is continuous, this is differentiable, it's polynomial. Now we move on. The last thing we have to do before we can use Rolle's theorem is we have to say, is f of A equal to f of B? F of -3 equal to f of 1. And how would we do that? Plug them in, sure. So f of -3, somebody hit that one for us, get that number, and then somebody else do f of 1. We'll knock them both out. Three minus 1, 1 plus 3 is 4.
-3. X is greater than or equal to -3, and 1 is greater than or equal to x. Could they be the same number?
Could x be the same? No. X is a number between negative. Okay, all right. They are equal. They both equal -1. So now we carry on. It says find all numbers C that satisfies the conclusion. So now we know we can use the conclusion, or we can use the theorem. Because they're equal, now we know that there's some value f prime of C that equals 0. Our job is to go find C. So what do you think we should do first? Take the derivative, derivatize. So f prime of x, yay, power rule. 3x squared plus 6x minus 1. Now we're able to take that derivative and set it equal to 0, and we'll be able to find the function. We don't plug in 0. Tell me why I don't plug in 0. Yeah, that would find your y value at 0. That's not what we want. We want to know where on this derivative is the derivative equal to 0. Anybody have any ideas? How do we do this? You could kick the 1. That would give you a really sad situation. Don't kick the 1, unless you're willing to complete the square. But you would have had to divide the 3 first. It's a quadratic. You could use the quadratic formula. We could do this. 3 times -1. Are there any factors of 3 and -1 that make 6? -3 that makes 6?
Yeah. -6.
I don't. No.
What was the question?
So I was looking for any factors of -3 that would make 6. That doesn't work either. Okay, so quadratic formula it is. -6 plus or minus a square root of b squared minus 4ac all to a.
That's the most helpful thing I've ever learned in math class.
You're welcome. Plus 12.
Actually, I learned that from the one and only dogs.
He sang to you?
No, you would just play the video.
Yeah. I was about to be really impressed.
There's no way.
Oh my God. Why is that happening?
2, 3.
I'm going crazy.
My mom used to sing me a crazy song. She would say, I'm going crazy. Don't you want to come along? I'm going crazy. Just to singing this song.
You okay, Seth?
No.
Okay, I'm about done. This is all I can do by hand. If you put them in your calculator, you got -1 plus 2 square roots of 3 over 3, which is what? Anybody did the plus option? C equals 0.15? 0.155? And we've got another one at C2, -1 minus 2 square roots of 3 over 3? -2.155. Okay. What I really wanted to be able to show you was the calculator image that goes with this, and I couldn't. But the picture that's at the bottom of your page on page 307 kind of shows you what happened here. It looks like it goes like this, except we land and begin in the same place. And so our values that we just found were here and here. Positive 1.55 and negative 2.55. This is graph not drawn to scale. Okay. If you looked at the derivative, if they graphed the derivative, what would you see in this place and this place? They would be x-intercepts. So that's the difference. I'm looking at the function here, and I see extrema. If I was looking at the derivative, I would see x-intercepts. Yeah? Questions? Anybody? Comments? Concerns? Why did we have to bring up the quadratic formula? Well,
He's concerned.
aren't we all? All right, here's example 2. Rolle's theorem and a position function. A position function. So this sounds physicsy. Suppose a particle moves along a horizontal line so that its position at time t is given by the continuous and differentiable function s of t. I feel like there had to be more to this. If the particle is in the same place at 2 different times, t equals a and t equals b, then s of a equals s of b. Using Rolle's theorem, there is some time t equals c between a and b that the derivative of the position or the velocity is 0. Okay, so there's really nothing to do here except kind of think about what's happening. This is a particle moving along a horizontal line. Okay, moving along a horizontal line. So this particle must be kind of just zooming back and forth right here. What it's saying is if its position at time A is equal to its position at time B, then at some point along its path, it hit velocity equals 0. At some point along its path, it hit a resting situation where it turned around. Otherwise, it doesn't end where it began. Does that make sense? It has to start and end. Well, it doesn't necessarily have to start and end at the same place, but it has to pass through the same place. It's on a horizontal line. So in order for it to get back to X, it had to hit somewhere V of t is 0 and turn around. Otherwise, it doesn't get back to that position again. So in order for it to have the same position twice, it's got to come to rest. Is that making sense? Okay. Otherwise, it just keeps going. It just keeps going and going and going. Cool? It's got to turn around. That's essentially what it's saying.
So there was actually no question.
No. So I would imagine if a car was on like Highway 60, traveling between here and Amarillo, right? What I'm saying right now is, let's say it passes through White Deer twice. If it passes through White Deer twice, it had to do what? It had to turn around. So there's some place where it turned around. And when it turned around, the derivative was 0. The velocity was set equal to 0 because it stopped and moved the other way. Otherwise, it doesn't pass through White Deer twice. It just... Okay. This is going to be example 3. Example 3. And it says, show that the equation x cubed plus x minus 1 equals 0 has exactly one real root. Show that it only has one real root. Oh, this is so much theory today.
We're not doing the mean theorem yet?
Hmm?
Or is this still the-
No, we haven't done the mean value theorem yet. No. Okay, so the first thing we want to think about is it continuous? Is this function continuous?
Yep.
Yes, it is continuous. Is it differentiable?
Yep.
Yes, it's a polynomial function. Okay, so it says since f is differentiable or polynomial, it is continuous everywhere. They tried a couple of different numbers here. So they said, let it be f of 0. Let's plug in 0 to this function and see what happens. If we do that, what do we get? F of 0 is -1. That puts me on the y-axis. Let's graph it. I'm good with that. On the y-axis at 0, -1. Try also f of 1. What is f of 1? 1 and 1 minus 1. So 2 minus 1 would be 1. F of 1 is 1. what are you using? He said, so somewhere in between there, what?
It's 0.
There is a 0. What are you using to make that determination? What is it called? He said, so somewhere in between, there's a 0. Somewhere in between, right? That's called the intermediate value theorem. So by the intermediate value theorem, intermediate meaning somewhere in between, right? By the intermediate value theorem, THM for short. By the intermediate value theorem, there is a 0 between f of 0 or between 0 and 1. Between x equals 0 and 1. And you know that because it is continuous. It's going to pass through every point between x equals 0 and x equals 1. It's going to pass through every point between f of 0, which happened to be negative 1, and f of 1, which happened to be 1. Okay? When we did this the first time, I gave the example, if we rattled off our test scores in this class, does that imply that one of you made a 75 if the test scores ranged from a 60 to 100? No, we are not guaranteed that somebody in here made a 75. Why?
Scatter plot.
Because it's a scatter plot. It's discrete data. I gave individual test scores that were represented by dots. So there's no guarantee that we included all of the numbers in the range of the test scores, right? But if I say Sophia turned 17 today, it is guaranteed that at some point in Sophia's life, from age 0 to age 17, she was 2. True?
Yeah.
Why?
Because 2 is in between.
Because it's a continuous age. Is that better? Okay. So that's the IVT. Because it says that there is a root, now we can use Rolle's theorem to show that there's only one root. I don't think we can use Rolle's theorem here because it contradicts Rolle's theorem, seeing as how we don't have the same values on A to B. So, and that's actually what it says at the end. This contradicts Rolle's theorem, so the assumption is false. The equation can't have two real roots because it never turns back around to equal the same number. Does that make sense? No, really. I know that was confusing. This is passing through only once. The function itself doesn't have any values where f of A and f of B are the same number. Rolle's theorem requires that. So the fact that this goes up and it's only increasing and it never starts decreasing again means that there's only this one real root. So the contradiction of Rolle's theorem is why we know that it has exactly one real root. Yeah? I'm going to take it. We're going to take the win. Move on. I don't know about it. All right, now this brings us to the mean value theorem. Finally.
On the entire page of mean value theorem, there is no mean value theorem.
There is a mean value theorem, and it's very, very helpful. The mean value theorem. So I'm going to give you time to write it, but the first thing that I want to talk about, we said that the word intermediate tells us I'm looking for values in between, right? I'm talking about values in between a range of number. Extreme value theorem tells me I'm talking about maxes and mins, right? The mean value theorem tells me I'm talking about an average. There is an average something involved here, okay? So I'm going to pause, and I'm going to let you guys write it down, and then we'll talk. Okay. And yeah, we took a break. Yeah. Okay. Hello.
I don't look like Ben Shapiro.
Listen. So this is the mean value theorem. Brooks helped us out here. He said mean is average. That's exactly right. Okay, so the breakdown here, it says if a function is continuous and differentiable, so we've got to prove both before we can use this theorem. But then if that's true, there exists a number c on the interval such that f prime of c, now what is that? F prime of c. That is the derivative. That is the instantaneous rate of change. F prime of c is the instantaneous rate of change. There exists a time where the instantaneous rate of change, and how was this guy? This is the slope, right? Secant line slope. y2 minus y1 over x2 minus x1. The average rate of change, there is some point in time where these two numbers are equal. This is helpful. Imagine that I'm going to Amarillo. Okay, I use this all the time. We're going to Amarillo. We averaged 75 miles per hour. I was in a hurry, and I didn't hit the red light in Panhandle. Didn't even slow down, it seems. Okay, 75 average miles per hour. Are you with me? I just going. The mean value theorem says that at some point during my trip, I went 75 miles an hour. So not only did I average 75 miles an hour on the total trip, but at some point during the trip, my odometer went through 75. That's the mean value theorem. Okay? The average rate of change at some point is equal to the instantaneous rate of change. There are some pictures in your textbook. A lot of times people think that that happens to be at the midpoint. That's a common misconception. That's not true. It doesn't have to be in the middle of that function. Okay? Another thing to look at here is if you write this out, f of b minus f of a is equal to f prime of c times b minus a. What is this? Can y'all recognize this? Yeah, y minus y1 equals m times x minus x1. That's point slope. That's all that the mean value theorem is saying. This point slope.
This is how they came up with the point slope form?
Maybe. So what we're saying is the changes in y's over the changes in x are equal to the instantaneous rate of change. At some point, that's true. Okay. I want to look at the pictures on page 309. On page 309. Okay, so we've got some function here where we've got a point a comma f of a. And we've got another point b comma f of b. Okay, and this function happens to kind of do a little whoopie-whoo like that. The average rate of change between these 2 points is the secant line that connects them. The average rate of change between these 2 points is the secant line that connects them. And we would do, in this case, f of b minus f of a over b minus a. Everybody, yeah? Okay. All right. The mean value theorem says that there exists some point on this curve where if I took its derivative, I would get the same number. That's as parallel as I can do on a graph. There is some point on this curve C where the tangent line slope is equal to the slope of the secant line. Okay. If you look at the next picture in your textbook, you'll see kind of the same setup. We've got some function, and what they're telling me is the rate of change from A to B is equal to the instantaneous rate of change. Looks like it happens at a couple of points here. Okay. So we're looking for parallel. When you start looking at your homework, they're going to ask you kind of where does that happen. I would take a straight edge and I would run it on my secant line and get the slope kind of figured out, and then I would use that up and down on the function to try to find where is that point where this slope is parallel in both places. Is that making sense to you? Yeah. All right. Let's call it a day. We'll do some more of these kinds of problems tomorrow.